for this kind of invitation, and many thanks to Carl for having a birthday. All right, yeah, I would like just also like Ron to start with some photographs. Yeah, so this is actually the first photograph of Carl that I have. Yeah, and so this was in Madison, very cold city. I believe it was 1995. Yeah, start of. Yeah. So with these two photographs, so this is Shane Valeron, yeah, who is here, right? Yeah, and so with these two photographs, you see what is the difference between a professor and a PhD student, yeah, and namely, so this photograph was taken by Carl, yeah, and this photograph was taken by Shane, yeah. What? Yeah, so that's the point, yeah, so this was taken by Carl, and then, so Shane at this point was not yet that experienced yet. All right, so I have a couple more photographs. So this one.
He's cheering for the Wisconsin Badgers. First down. Another Badger first down.
No, okay, so it seems that there's nothing written just on the whiteboard, yeah, or blackboard, yeah. But anyway, so this photograph is taken is constructive theory of functions in Varna, yeah. So what I like about these photographs is that it was not me who took it, yeah. So this photograph was on sale, yeah, at this conference, yeah. And I bought it, I believe, for, I don't know, $10 or something like that, yeah. So it was not that cheap.
But notice he has not changed much.
Yeah.
In 12 years, right?
Right, yeah.
About the same.
The same short? No.
Not the same short, but he looks about the same.
No, but anyway, so I bought this photograph, and I know that I read these stories maybe in Aachen already, yeah, so that in the past, at the late 19th century, beginning of 20th century, yeah, so the photographs of professors, yeah, so they were on sale just at the university kiosks, yeah, so you can buy them like, I don't know, photographs, I don't know, Beatles, Rolling Stones, whatever, yes, Marilyn Monroe, yeah. And so this is a kind of the photograph, yeah, which I bought, yeah, so that's. No, that's already been. Maybe two, yes. Yeah, okay, so that's myself and Carl, and I don't know. So it's year 7. Yeah, what was that? I'm not sure what we had. So probably it was also the conference in Bulgaria. Yeah, so this photograph. Yeah. All right. So that's Alan. Yeah. So he was.
Drank too much.
No, he simply just tried to spoil the picture. Yeah. So that's we have. Yeah. So it's me and Carl and two beautiful girls. Yeah. And then Alan is here, right? Yeah. All right, and probably one more. This. Okay, so this was Carl's Fest in 2003. Yeah, and I'll show the picture where it's not myself. It's been here. All right, so then, oh yeah, so they. And this.
What have we heard about Tikhomiro? Does anybody have news about him?
No, I don't have any news.
I haven't heard about him for a long time.
All right, so this is the Russian mafia, and so it's myself, and then Tikhomirov, and then Temlyakov just is on the edge. What? So yeah, that's Temlyakov. Yeah, so that's Temlyakov. Yeah, Temlyakov here. Yeah, and.
Where was this?
No, this is Carl Fest in 2003 in Dagstuhl. Yeah.
Oh, really?
Yeah.
It's not in Moscow?
No. And actually, well, the photograph which I showed before, I mean, with myself and you, well, not with where Alan is. So Alan is a different occasion. Yeah, but do I have maybe some anything else here? No. No, 7H, no here, right. So that's it, yeah. So So this photograph, again, so it's from the fest, yeah, so that's from 2003, yeah. All right, so now I'm ready to go to my talk. And there will be some other pictures as well, yeah, from the... All right, so I'm going to talk about de Boor's conjecture, past and present. So this is a summary of my talk, so I will give some key definition and statement of the conjecture, and then just I will go just about the initial points of interest. So Ciesielski was probably the first who studied the orthogonal projection onto splines in '63. So then Karl studied it again with respect to interpolation problem. Ciesielski was interested in construction, just orthonormal basis, yeah, and then Douglas, Dupont, and Wolbin, so they made some progress while studying Galerkin approximation to 2 points boundary problem. Then I will just give some key ideas of my general proof that I found, and then I will list the new result. Yeah, so one might think that the conjecture and everything related to this one just has died just after my proof. Yeah, but it's not the case. Yeah, so there was certain activity in the past. Yeah, so Foucault, who was my student at that time, just made some progress, and actually, well, Karl de Boor himself just made some cleanup just with respect to my proof. So then Volkov from Novosibirsk, he studied unconditional convergence of spline interpolants. So Peter Oswald contributed to splines on triangulations. And then finally, so Manfred von Golicek, he found this simple proof in 2014. And I contributed myself, yeah, with a joint paper with Markus Passenbrunner from Austria, and we proved convergence almost everywhere. Yeah. Okay, so that's my definition. So we have a space of splines of order k. It's degree k minus 1, just on the knot sequence delta n. So those are piecewise polynomials. And this is a knot sequence where they have the breaks just of the polynomial structure. Yeah, and they are the smoothest splines possible, so they belong to the space ck minus 1. So we consider PS, so the operator of orthogonal spline projection onto S. This satisfies this property that the scalar product is the usual standard scalar product integral of f, whatever, fg. And so this should be true just for any sigma from the spline space S. Yeah. Of course, the norm of the orthogonal projector is equal to 1. Yeah, but then we're interested in this norm as an operator from L infinity to L infinity. And de Boor's conjecture is that for any k, so the max norm of the L2 projector onto spline space Sk with any delta n is bounded independently of delta n. So this is
The polynomials, if you go back one slide.
Yeah.
Ck minus 1, that's just a polynomial space.
K minus 2.
K minus 2 probably. K minus 2, yes. Yeah. So degree k minus 1, so this, the smoothness is k minus 2, yes. So linear spline k equal 2. So then they are just continuous, yeah, right. Okay, so this conjecture, and well, okay, I will say about it just at the very end, one more time. So that this supreme, that this orthogonal operator of this orthogonal spline projector is bounded just independently of the knot sequence. And this appeared in 1972 and was attached with the following statement. I offer the modest sum of m minus 1972 times $10 bills to the first person. Communicates to me a proof or a counterexample, but not both, of his or her making of this conjecture, known to be true for k equal 2 and 3. And here m is the year of a d of such communication.
Are you sure that you put the dollar on the right of the 10? You should have put the dollar on the left of the 10.
I think originally it was $10 bills, yeah, so I somehow just shortened it.
But the dollar should be, the sign should be on the other side.
Yes, normally, yeah.
Otherwise it's not Karl. It was offered by somebody else.
Right. In the original statement, it was not the sign of the dollar, but it was written dollar bills, yeah, so I somehow just trying to preserve Karl's spirit, yeah. So anyway, so modest sum, first person, just very clever, just formulation, very clever, just thoughtful, yeah. First person, yeah, because many persons can communicate, yeah, just proof or counterexample, but not both. And then his or her, just already 1972, just very this, how one can say, friendly, tolerant, yeah, his or her making of this conjecture. And here M is the year, AD, so because here M minus 1972, so no way just somehow just to claim it with respect to, I don't know, Chinese calendar, right? Where you have 6,000 or whatever. So that was the conjecture. All right, so what was known initially and, well, not initially, so this was, I mentioned it already, so Krzyzewski was the first construction of orthonormal basis, general Franklin system, unconditional basis, and so on. So Boor in 1968, so his interest was error-spline interpolation, conditional number of B-spline basis, cardinal interpolation, and so on, and Douglas, Dupont, Wolbin, so they started with Galerkin approximation, and then somehow not just, it's not their result, but they somehow just what they achieved was developed by Demco and others, exponential decay of the finite approximation of finitely supported function, exponential decay of fundamental splines, and so on. So that's what Krzyzewski was interested in. So we have the Faber-Schauder system, and those are the systems. So the first function is just a constant. The next one is a linear spline, is a linear function, and then so this is a head function, and then we just split it into just binary sequences, and then we obtain just further elements of the basis. So this is the basis in the space of continuous function, not in LP. And if we orthogonalize it, this system, then we obtain what is called the Franklin system, which is obtained by orthogonalization just of this. And this was the first, I believe, unconditional basis in LP. Or maybe the first even basis just in LP, which was just orthogonal. So anyway, so the splines which were, what?
Trig polynomials are non-conditional basis
What?
in LP.
What?
Trigonometric polynomials are a non-conditional basis in LP.
Yeah. Right.
Okay.
No, but I mean, those systems just appear, all right. I will not go into these details. So, but those are actually just the B-splines, so the splines, piecewise polynomials, and if you consider just approximation by Franklin system, we actually obtain just spline, orthogonal spline projector just on the space of the splines and the spline and the span of this phi I. So this is actually spline function. So we're considering the best orthogonal approximation. So what we are doing, we take any basis. So if S is expanded in this basis in this way, so then we just run in this sigma through the elements of this basis, and we obtain what is called just normal equation. So it's JA equal B, and G is a Gram matrix. So B is a product F and UI. So basically, just we need to solve the linear equation, linear system of equations, and then we obtain this solution, the coefficients of this AJ. So this again the linear B-spline basis. So what we need to do just in order to estimate the orthogonal projector, so with respect to the L infinity norm, so it's more convenient to consider renormalized Gram matrix. Now we just multiply one part with one constant, another part with another constant, and so we have two bases now, just N and M. So both are B-spline bases. And so this one forms a partition of unity, and the next one is just integral equal 1. And then, so now with these two matrices, so we multiply it with Mi, and then we're getting this Gram matrix. Now those are coefficient, and this is what we're getting. And so we have, because now, so this norm is less than norm of A, because of spline forms partition of unity, and this B is less than the norm of F because M is integral equal to 1. So we're getting the bound for the coefficient, so A infinity is equal to the norm of the inverse times the right-hand side, and respectively this equation, so the norm of the orthogonal spline projector can be measured just in the norm of the inverse of the Gramian inverse, and now Gram is this matrix. And actually what what Boor proved is that we have both, it's not only the upper bound, but also the same lower bounds with a constant which depends only on k, yeah. And then he wrote in his paper that, so therefore measuring the norm of the orthoprojector, we're measuring the norm of the inverse, whether we want to or not, yeah. All right, let's see how Chiselsky result, actually he did it first, just somehow, how this is materializes in this form. Yeah? So this is a matrix which I easily computed just with respect to linear splines. Yeah? So, and one can notice that this matrix is diagonally dominant. Yeah? And then the elements in the row, they've been summed to 1. I mean, these off-diagonal elements. So here the sum is 1, here the sum is 1, here the sum is 1. So therefore, 2 minus 1 is 1. So here is coefficient 1/3. Yeah? So therefore, so this matrix is diagonally dominant, and therefore, with coefficient 1/3, with a constant 1/3. Yeah? So therefore, its inverse is bounded by 3, by the inverse of gamma. Yeah? So this is a well-known result, which probably goes back to Gershgorin himself. Yeah? So anyway, so we have for orthoprojector onto linear splines, we have the bound equals 3. And everything is very easy. All right, so now we try to a little bit to generalize. So how to relate it with the spline interpolation problem, because now we next move in what Carl de Boor was interested in this projector, just what is the connection just with spline interpolation problem, yeah? So now S is the spline of the order 2k, degree 2k minus 1, and it's interpolate the function at the points of at the same break points just of the partition, yeah? And then it is known that, that the orthogonal projector just of k's derivative of f would be just the k's derivative of interpolating spline, yeah? So that's the result. So this is because of the fact that B-splines form the piano kernel just of the divided differences, yeah? So therefore, so this scalar product is equal to the divided differences of f. S take the same value. It's divided difference of s. So therefore, it is this form, yeah. So and respectively, because mi are running through all spline space, yeah. So sk is now just orthogonal projector of k into the space of splines. All right. So therefore, what we can get, so this difference is this difference, and now Lebesgue inequality, and this is the best approximation of fk by splines. So if we know that this is bounded by some constant, then we can use some elementary estimate. So if this difference is vanishing, so if function have many zeros, then it can be estimated through its derivative and times the maximal step of the partition. Yeah, so we have two types of the estimates. The constant still depending on this p, which we don't know whether it's bounded or not. Yeah, but one estimate is that the highest possible. Yeah, so splines of order 2k, degree 2k minus 1, and if the function is 2k times differentiable, then it's h to the power 2k, the order of approximation. Yeah. And if we're approximating just in terms of fk, then it could be just omega k can be put here. Yeah. But again, so here the constant, they depend on this one, yeah. And so Karl's motivation was just to prove that this is bounded, and therefore to get this bound and that bound, yeah. And to the extent I can tell that actually, so this can be achieved without de Boor's conjecture, yeah. And I did it in 1989 to 1990, yeah, without proving the conjecture. This was my starting point of interest, yeah. So I wanted to get this one. I was interested in the orders of approximation by spline interpolation. Yeah. So and I got both two results with absolute constant. Yeah, which depends on k, just without any approach into de Boor's conjecture. Yeah. Right.
So h is the maximal distance.
Yeah. H is the maximal distance between the nodes. Yeah. It's like, well, this kind of result is. Can be related, say, to the Chebyshev polynomials, yeah, and it is known that the Chebyshev he invented his polynomials not because of any just kind of approximation problem, but simply he was studying the Watt steam engine mechanism, yeah, and he was actually just studying how you can translate the rotational movement to the horizontal movement, yeah. This is how he invented, yeah. And then actually 5 years after that, so another engineer just found another different combination of all this connection, yeah, and solved the problem completely, yeah. So in that sense, the problem, the initial interest just of Chebyshev and like Chebyshev polynomials was probably killed instantly, yeah. But nevertheless, so Chebyshev polynomials are still here. In that respect, that I mean the fact that so those estimates were proved just without using de Boer's conjecture, so it doesn't make the conjecture disappear. Yeah. All right, general case. Yeah. So here now it shows the quadratic spline. So we now just again expanding our projected just splines degree k minus 1, and we have the same estimate. Yeah. So this is 2 because not correct. It should be k here. So for any splines. Yeah. And now the problem. So the problems are immediately there because now just unlike the Chiselsky result, yeah, so the matrix is not diagonally dominant anymore, yeah, and so some other tools should be found, yeah. And this tool was the total positivity of the matrix, yeah. So the first result was theorem, so proved initially by Karlin, and then de Boer found a simpler proof. So for this Gram matrix, the inverse is totally positive, meaning that all minors of this matrix are non-negative, yeah? And de Boer noticed that the matrix then inverse is checkable. It has the following sign structure. So plus, minus, and this follows simply by the Cramer's rules, yeah? So this is a formula for the element of the inverse. So here the sign is minus 1 to the power I plus j, yeah? And then all the determinants are positive, so therefore the sign has this structure. All right, so this is a lemma by de Boer, and it said that if H is checkable matrix, and we have 2 vectors, in order to find the element, the norm, the estimate for the norm of the inverse, we don't need just to investigate the structure of the inverse. We need just to find actually one vector A, yeah, and so such that HA is equal to B. So now if B alternate in signs, and it is bounded from below, so then the norm of the matrix is estimated by the maximum of A divided by this minimum of B. Yeah. All right, so here is the proof. So AI is H inverse B. So those are these elements. And so the path from here to here is because so the sign of inverse alternating, and B, sign of B is also alternating. So therefore, we can put the modulus inside, and then we just proceed to this inequality, and this is the norm of inverse of the H. Yeah. So this is a way just to estimate it. Yeah. So now let's see how it works with the Chiselsky case, which is a simple one. Yeah. So this is the matrix. We take simply just vector 1 minus 1 and so on, and so result is just 1/3 of -1. So this is A. So this is B. We take the maximum of A, divide by the minimum of B. Now B is 1/3, yeah? So we get 3, and again the same Chiselsky bound. Yeah, works brilliantly. But again, so the problem is what we do when we move from linear splines to splines of the higher order. All right, so in 1968, yeah, so Karl suggested the following, just algebraic choice of the element, AI, yeah? So this was the expression, yeah? Just so support of MI is Ti plus 3, yeah? So these are the difference of the last point of support, and then second point, last but 1, and the first point, yeah? So approximately this kind, yeah? And then he proved that the following upper bound just simply by computing what will be the result of Gram matrix acting on this AI, and then bounded from below. And already for quadratic splines, so it was very difficult to compute the entries, yeah. And actually, Karl himself in 1968, he made arithmetic mistakes, yeah. And then he had to repeat this calculation in 1980, yeah. And many pages of calculation, very just tedious calculation. And I don't know whether there was anyone who refereed your calculation. Anyway, but I did, yeah. So anyway, so it was, but I did it, of course, not in 1980 or whatever, yeah, because it was impossible and will not have this stamina to do it, yeah. But then in well, by the end of the 90s when Maple, yeah, and then these packages of symbolic computation appeared, yeah. I simply took this expression, put them in, yeah, and then, so the constant is given 30, yeah, you subtract the constant, expand in positive terms, and positive terms are these steps. HI, so that's true, yeah, so I did it, yeah, so I checked it. And I believe also I improved maybe both constant, maybe one of them, yeah, from 30 to 29 or something like that, yeah, so this was correct, yeah. But it was also clear that you cannot do just quite far with it, yeah. So this was published in 2 papers, actually. The computation for k equal 4 never appeared, yeah. Okay, so even with the Maple, yeah, so what would be this formula further on? Just I asked Carl whether he had some insight, just what, I mean, how can you generalize this, yeah? But even if you generalize it, so therefore just for each k you need to check it, yeah, so you cannot do it for general k. All right, so this is what Douglas, Dupont, and Wolbin did. So they started with a 2-point boundary value problem, just in the weak form. This is Galerkin approximation. And they wanted to approximate solution, yeah, on the assumption that it belongs to the solar space WK infinity, yeah, with the splines, just by considering this Galerkin approximation to this weak form of the solution, yeah. When it was from WK2, yeah, so the order was k minus 1/2, yeah, they wanted somehow just to get the order for the function whose k derivative is bounded just a bit higher, yeah. And then they proved that basically, so for their result, so the main tool was that if the partition is quasi-uniform, yeah, so if the largest step divided by the minimal step is bounded by some constant m, so then, so this the projector onto the space of splines, yeah, which was taken by these spaces, yeah, is bounded by ck. Yeah. So what was interesting is that so it became clear that so their proof it doesn't depend on any properties of the splines, piecewise polynomial structure. What they used is that the basis of the function is finitely supported, yeah, and then it has a good condition number, yeah, and later on, Demco eliminated even the basis and reduced everything to the statement about the band matrices. Yeah, so this is a statement by Demco Theory. Yeah, if A is a band matrix, yeah, so this means that all elements of certain band of width R are 0, and then if the norm of the matrix and its inverse is bounded, so then the elements of the inverse decay exponentially away from the diagonal. Yeah, so that's very, very beautiful theorem. So what it gives us, so now we just consider the basis which is normalized in L2 norm. So this is our Gram matrix. Gram matrix will appear here, yes. So we now know, so this is a expression for which somehow just give condition number of the B-spline basis, yeah. So we know that AJ, the sum of these satisfy, so it's a kind of the risk basis, yeah. So this is a constant from above and from below, yeah. So then we can write it in this form, and this means that the matrix G hat, yeah, so it's bounded from above, and its inverse is also bounded from above by the constant which is independent of the size of the matrix, yeah. So respectively, then the norm of its, the element of its inverse, they are decaying exponentially away from the diagonal, yeah. But we need not this basis, not L2 basis, but L1, L infinity basis, but those goes just simply by multiplying so these terms, yeah. So the maximal over minimum, yeah, so will appear here. So we got to this ratio. Yeah. All right. So this was what done just more or less with respect to the general result just by 1966. There were several further results by Herlich and by Ron Kwanzia about the geometric meshes, yeah, because, well, geometric meshes were the meshes for which spline interpolation procedure diverges for the function of the slow smoothness, yeah, of the lower smoothness, yeah. So there were some attempts to prove or disprove, give some further proof confirmation for the Boor conjecture or disprove it, yeah, on geometric series. And anyway, so so somehow just in the 90s, I started to interest in this problem, yeah, and not least because of this M minus 1972 times $10 bills, yeah. All right, yeah, so general proof, yeah, it's very easy to prove the Boor's conjecture, and I know it from my own experience because I did it many, many times, yeah, so that's... What?
How many were correct?
That's the point, Ron, yeah, you need explanation, right? Yeah. Okay, I'll show you one more picture. So how can I rotate it? Yeah, could you help me? I don't see. View. Rotate. Clockwise. Right, okay, yeah. Right. Okay, so okay, so one day I came back home, yeah, and said to my wife, today I proved the Boor conjecture, yeah. And she said, what? Again? And I said, no, you cannot claim that. I never claimed that I proved it. So previously I was saying that I think I was proving it. And she said, no. And she said that I will take a photograph of you, yeah, so that the next time, yeah, when you came, yeah, so I will show it to you, yeah, so and that's photograph, yeah, so but then it turns out that so the next photograph was not necessary, so yeah, that's actually just very seldom, very rare event, yeah, when you can somehow just be just photographed and the way just how you when you got the idea right, yeah, so that's.
So you were thinking back then about the fame as professionals that you are going to get, or about the money that you are going to get? So what did we do?
No, happiness, no. Happiness is just to prove a conjecture. That's the happiness. Happiness is a proof mathematical statement. So there is nothing. I'm not here happy not about the money, not about anything. Yeah.
This proof turned out to be correct.
Yeah. So this was taken just shortly, just before or after Christmas. It was 1999. Yeah, New Year, 1999. Yeah.
And all the other photos that you took before, you deleted them.
No. That's it. So this.
Did you always wear the sweater when you had these?
What?
The same sweater that I saw in other pictures. Did you wear that same sweater on the?
It's the lucky sweater that he started to wear.
The lucky sweater.
Right. No, it was. I mean, this was in Aachen, yeah. So Wolfgang somehow witnessed my proof, yeah. And then I remember I was taking my children to Taekwondo, yeah. And then yesterday we discussed whether just in Karl's period, yeah.
Have you proved the conjecture when you were in Aachen?
Yes. I was in Aachen, and not only that, I proved it. I was on the bus bringing my children to Taekwondo, yeah. And
Probably Wolfgang proved this conjecture.
Yeah.
Maybe Wolfgang proved it.
No, he proved it. No, Wolfgang just was somehow just how one can say just.
Encouraging.
No, Wolfgang put my children into Taekwondo, and then I brought my children. I was in the bus bringing my children to Taekwondo, and then while sitting in the bus, yeah, I realized how one can do it.
That was an inspiration.
Yeah. So without Taekwondo, nothing would have happened. Yeah. So anyway, so as I said, so it was 1999. Yeah, and then so somehow just I sent actually just an email to Karl just in 1989 that I solved this. Well, not solved, but simply interested in whether the money are waiting for me. Anyway, so I realized that just rather quickly in 1990s, yeah, in the beginning of the 1990s, that there is no way not anyone can prove the Boor's conjecture, yeah, because so all the counterexamples, geometric meshes, they say that the conjecture is true for them, yeah. And to find a counterexample, it's impossible. Yeah, it's impossible to find the counterexample. It's impossible to find the proof. Yeah, I've never thought that I would prove it, yeah. But I wanted to prove it, yeah. So therefore, when I prove just kind of some small results, yeah, and I thought, why shouldn't I put the title "Proof of Divorce Conjecture"? And it was different divorce conjecture, yeah. And then I proved just one more result, and it was now just about multivariate case. And I thought, okay, so I will never prove the right one. Why should I put another divorce conjecture in the title? Yeah. And I have another paper just with divorce conjecture, yeah, in the title. And then when I luckily just proved this one, yeah, and I again had to put the divorce conjecture in the title, yeah. So I have just.
You could have put the real.
Yeah, maybe, right.
Did he really say that?
Well, he would have said, yeah, so I.
Did you say that, Carl?
That was the indication that it didn't come from you.
All right, so I had 3 papers. In 3 papers, it was the proof of divorce conjecture. Yeah, so that's a bit kind of disappointing. Yeah, I would say. All right, let's go back to the talk. All right, so general proof. So I took the analytic version of the Boor approach, yeah, and so this is about now. Just the time is running out, yeah. So I have well the same kind of the relation, yeah. Just and then it has quite this obvious indication, just quite an obvious connection to what Carl did, yeah. But this was analytic, so instead of thinking about just designing this coefficient, yeah, or something, yeah. So you start to think just what is a function which you need to invent, yeah, and this turned out to be the function which is a null spline, yeah, null spline of a certain degree, yeah, and so this is a null spline, yeah, of degree 2k minus 2, yeah, and then it has certain boundary condition, yeah, it's 0 boundary condition, it's 1 normalization, yeah, and the point is that. So when you just take a scalar product of this function, if you take the k minus first derivative of this spline, yeah, with b spline, so this phi is the k minus first derivative, but then you can integrate by parts, yeah, and all the non-integral terms, they will vanish, yeah, either because this is 0 at the end, yeah, or if you move to the end where b spline is non-zero, then spline is 0 at the end, yeah. So you can go to the different. So now here k minus first derivative and here the spline itself, yeah, but k minus first derivative of the b splines is alternate, yeah, and if you move it from one set to the next one, so then it will be the different now, yeah, and this is the same sign pattern for the spline, yeah. So therefore this product, yeah, which was the main problem, yeah, to find out that this is of the same, this alternates in sign and bounded from below, yeah. So this sign is minus 1 to the power I, yeah. So it follows almost immediately, yeah. So to find this one, so was just very good. So this was the main idea, yeah. And then what somehow just particular cases, so when k is equal to linear spline, so sigma is quadratic null spline, so its derivative is a broken line, and this is just the sum of, again, this Krzyzewski result, yeah. So it's a broken line which takes the value plus minus 1 in the node points, yeah. And another one with no interior points, yeah. So when this spline will be just Legendre polynomial, yeah. So this is also just the case which somehow just helps just to understand what's going on, yeah. And this spline has just very particular feature. It's orthogonal to the splines of smaller degree, yeah. So that was the main idea. Okay, so I'm moving now to new results, yeah, and so what happened just afterwards, just after I proved it, yeah, and then, so Simon Foucault, so okay, so it was Carl who proved that norm of the projector related to the norm of the matrix, ground matrix in this way. However, so these numbers are very large. Yeah, it's 2 to the power k. Yeah, so it's 4 to the power minus k is here. Yeah, so those values are somehow, they show that this, at least from these two relations, yeah, so you cannot say that anything good about this and that. Yeah, and for k equal 2 for linear splines, so both values are the same. Yeah, but what happens just in difference when k is not equal to? Yeah. And perhaps when there is no interior nodes, yeah, so then there is an indication that this is small and this is large, yeah. So when there is no interior nodes, then this orthogonal projector is simply projected onto the space of polynomials, yeah, and this is of the order square root of k, yeah. And the norm of the inverse of the matrix can be computed in the case explicitly, yeah, so this is the order 4 to the k, yeah. And then I conjectured in my paper that actually, so the exact bound for the projector is 2k minus 1. Yeah? I proved that it is lower bound, yeah, and I conjectured that it is upper bound as well. Yeah? And for the norm of the matrix, actually, well, this is also the upper bound, yeah, but they are of different order. Yeah? And then I gave this problem to Simon Foucault, who was my student at the time, yeah, and with some of the approaches which I just developed. Yeah? And he showed that indeed, yeah, for splines, he didn't manage to do the general problem, yeah, but the splines of the smoothness 1 and 2, yeah, continuous and then differentiable, yeah, so the order of the projector is still square root of k, and while the matrix is still of the order 4 to the k, yeah. And then he also just gave some insight, so what these values would be, yeah, so the lower bound, so what is this 2k minus 1, where it comes from, yeah. So this is some constant, and this rho is actually the orthogonal projector on the space of incomplete polynomials. Incomplete polynomials who start, say, on the interval 0, 1, not with 1x, x squared, but say with x squared. Yeah, so the certain power are missed. Yeah, so it's incomplete. Yeah, and then he suggested, although that this value is also not known. Yeah, so this should be the order of these projectors. Yeah, so if we are just projecting on the space of splines of degree k and smoothness m. Yeah? So if m is k minus 1, yeah, so then you will get about this order 2, order k. Yeah? All right, so by infinite and periodic cases, so in my paper just I mentioned this as particular examples, and that for by infinite case, I can use observation that all finite submatrices just of the infinite matrices are uniformly boundedly invertible, yeah, and so must be the matrix itself, yeah. And then in around 2011, yeah, so no, I now forgot the name. Saakian, yeah, Arthur Saakian. So he just sent me the paper of his student dealing with the periodic splines, and I replied to him that it follows from my result, yeah. And then he asked about details. I said that it's my paper, it's just only a few words. And then I started to think about it, yeah. And then I realized that actually I didn't prove it, yeah, because, well, my proof was about the finite section, but my finite section was not quite of the form for which my proof is applicable, yeah. So because I prove it for the sequences which are k-complete, so the endpoints comes with the k multiplicity, and the finite section, the points, they don't have such multiplicity. So I wrote to Carl about this, and also I couldn't find the reference to this path. Yeah, so Carl somehow recovered the reference. I believe initially it was some paper with Carl, Ron Kwanzai, and Alan Pincus as well. Yeah, and so Carl was managed just to do that. Yeah, and I will mention it later. Yeah, if I have time. So basically, if one knot sequence is a part of another, yeah, so then the inverse of the matrices, they have a certain correspondence. Yeah. All right, so unconditional convergence of spline interpolant. So Volkov. Okay, so there was certain cases. I probably missed. I probably go further. Yeah. So now. Okay, multivariate case, yeah, so so the case when you have tensor product is almost trivial. So Peter Oswald studied the case when just orthogonal projection on triangulation. He found that now the Boor conjecture is not true anymore, that it is bounded below from M. Next, he made another conjecture that is bounded above also by big O of M. But generally, so it's not true. Yeah? In multivariate setting, it's not true. One need to think the same is about what is called multivariate thin plate spline. Yeah? So one need to think about some other settings just in order to find some more or less similar result. Yeah? So now short proof by Golicek. Yeah? So in 2014, he found a short proof, and his main point was that it's enough to prove that this projector is bounded only just at the end point. Yeah? So this is the value of the projector at the end point. Yeah? And then in the next step, he showed that if it is bounded at the end point, it is bounded in the first interval and the last interval, and then the general projector can be combined as just as a half interval projector on one half interval and then the other half interval. So that's what the idea. Yeah? And then I was okay. So I like the fact that somehow just satisfied that my results are still being used. Yeah. So in what he was doing. Yeah. And so in order to prove that, so this is bounded. Yeah. So he first considered the spline, which can be as kind of piano kernel for the value of the spline. Yeah. So we have a splines which for any s gives a value functional at t naught. Yeah. And then if it has the B-spline expansion, then these signs alternate. It can be shown. Yeah. And then the norm of this spline gives the value of the projector, and this is of course because of that. Yeah, bounded by that one. Yeah. And then so this is my spline. Yeah, which I constructed. Yeah. So the value is 1, and then the scalar product alternating sign and bounded from below. Yeah. And then, so using this spline and this my construction, yeah, so one can prove. So that one, yeah, so 1 is equal this value at t naught, so this is a q naught f, q naught phi, and this is now just because q naught is ai, so this is this one, this alternates, signs alternates, yeah, so it goes like this, yeah, so we're getting the boundedness of the projector just at the end point, yeah. Okay, so insight in his proof, yeah. So there were several attempts to prove that. So all we need, yeah. So that is just, as I mentioned, with the Douglas dipole and Wolbin result, yeah. So all we need is a basis with a finite support, and then with a Gould condition number, yeah. But it is not enough, yeah, so one can construct counter examples that's not enough for the boundedness of the projector, yeah, but from the Golicek proof follows that it's enough to have just the boundedness at the end point, yeah. If you have, so what is a generalization of von Golicek result, yeah, if you have the space which is finitely supported and then good condition number, then if it is bounded at the end point, then it is bounded everywhere, yeah. Bounded on the whole interval. Yeah. Well, for another Chebyshev system, say again, so to prove that it's bounded at the end point could be a problem. Yeah. But anyway, so that's at least it gives something which allows to get the general result. We also prove convergence everywhere, just with Spassen-Brunner, and then I move to the final touch. Yeah. So this was conjecture as I formulated it just at the very beginning on the very first slide. Yeah. So this was the conjecture. Yeah. So that I intend that I was going to prove. Yeah, and I prove it. Yeah, this is true indeed. But the exact wording of the original conjecture was different. Yeah. So if you look at the original paper, it was not about spline projector. Yeah. First, Karl proved that spline projector is equivalent to the evaluation of the norm of the matrix. Yeah. And then his conjecture was to prove that the norm of the matrix is bounded, yeah. And the point is it's true for any knot sequence, and I proved it only for complete knot sequence with multiplicities, yeah. And then when we were discussing, so this with by infinite case, periodic case, so then actually just Carl realized that I didn't prove his conjecture. And then he sent to me this email just asking just something like, and then he added, I do not intend to make this an issue. Which reply, Carl, I have already spent the money.
He wasn't asking for a reason.
What?
He didn't ask you for a reason.
No, that's what he wrote, yeah. So therefore, somehow to prevent anything, I said that whether he intends or not, yeah, whether he do not intend, whether he doesn't intend or doesn't intend, yeah, I've spent the money. Anyway, but then, I mean, just Carl found himself how to fill the gap, yeah, and then, so actually, well, he found this, so the theorem which actually goes back to the Boor giant pincus, yeah, and that's what was mentioned, yeah, so the portions of the positive definite matrix, or not positive, totally positive matrix, yeah, so they are inversely smaller than the original matrix, yeah, so therefore, if the sequence is a finite knot sequence is incomplete, then we can embed it in the k-complete knot sequence, and for any such choice, yeah, so we have this one, yeah, so therefore, it somehow follows from my result, yeah. Okay, so some open problems, and okay, so it's only one open problem so far, yeah, so which I put there, yeah, just to prove that, find the order of the projector, yeah, so that big O of k, well, actually the exact number, 2k minus 1, I gave it as well, yeah. So maybe just as the case to start with is just to find out what we have for the uniform partition, yeah, for the norm of the matrix is pi over 2 to the power 2k, and to find out whether for the uniform partition we have something like big O of k. Yeah, for periodic case, it's also interesting in periodic case because when power of splines delta n is fixed, degrees of splines goes to infinity, then splines become trigonometric polynomial, and then the order is log n. Yeah, so it's also just somehow just moderate growth. Yeah. All right, now maybe just again, so about this conjecture, which I wrote, and everybody actually wrote it in the wrong way, and Carl himself wrote it in the wrong way. Yeah, and I will show it now to you. Okay, so I've got the money at the end. Yeah, so that's. No. So that's the check, yeah. And now you see that he wrote to me for proving this, yeah. So he didn't mention his original conjecture, yeah. So he gave me the money for proving this, yeah. You have actually the date, yeah, the actual date, yeah. And then 440, yeah. What? By the way, so that's. So the sum was, I will now just go to the explanation why the sum is 540, yeah, but the point is that the sum was, if it were 270, yeah, as promised, yeah, then I probably will put it in the frame on the wall, yeah, and would not touch it, yeah. But 500 was too much for me, yeah, so I had to cash it, yeah, so I don't have this check anymore. So it's a bad negative sign. Positive sign that I cash it to Carl, yeah. And maybe he still has this check. Yeah. Do you have the check? Do you have this check? I gave it back to you. I cashed it with you. You don't remember it?
Oh, I can tell you, I also have an account with this bank, and you have a copy of the check. He has a copy with him. Don't worry about the checks that he gave.
No, Carl should have original. Yeah, so that's. Okay, I'm finishing in 1 minute. Don't worry, full screen. All right, who is the nice guys? Yeah, so that was the offer of Carl, modest sum, this and that. I proved it in 1999, and should have got 270, but got 540. So the question why the sum is twice is promised and the modest sum not, and the question is who is the nice guy? Is it me or the Boor? But not both, yeah. But not both, yeah. So that's but not both, yeah. And the answer is that the nice guy is Ron Kwanzaa. And actually, Karl de Boor said that about 5-6 years ago, before 1999, on some occasion, that given inflation and all that, I must double in rate. And in fact, Ja was kind enough to remind me about it. Yeah. All right, yeah. So thank you all, yeah, and thank you, Karl, for everything, yeah, and I'm very grateful for everything you have given to me, and especially for Czech. Yeah, so that's okay.